Welcome back to the class on electromagnetic field theory. In this lecture, we are going to discuss about the modified Ampere circuit law for time varying fields. In a static electromagnetic field, according to Ampere's law, curl of h bar equal to j bar. Now you take the divergence on both sides. Divergence of curl of h bar equal to divergence of j bar. Divergence of curl of h bar value becomes a 0. From the continuity equation, divergence of j bar equal to minus dou rho v by dou t. From the three equations, we can say very clearly that the divergence of j bar equal to 0, then only the equation 2 is true. The equation 2 and 3 is not compatible to the time varying field. So, in place of j, we are adding the one more term, that is n bar. So, the equation 1 we can write it as a curl of h bar equal to j bar plus n bar. If we take the divergence on both sides, once again, the divergence of curl of h bar, again this value becomes 0. The divergence of j bar plus divergence of n bar should be equal to 0. We know the value for the divergence of j bar, that is equal to minus dou rho v by dou t. Now the sum becomes a 0, then the divergence of n bar should be equal to dou rho v by dou t. We know that rho v equal to divergence of d bar. D bar is nothing but a electric flux density. So in place of rho v, in equation 5, substitute this quantity and simplify, we are getting the divergence of n bar equal to divergence of dou d bar by dou t. Both sides divergence are there, you remove the divergence, then n bar equal to dou d bar by dou t. So in this place, you substitute the n bar value. So we are getting the curl of h bar equal to jc plus dou d bar by dou t. Jc bar is nothing but a conduction current density. Dou d bar by dou t is nothing but a displacement current density. Conduction current density is nothing but the current which is passing in the circuit due to the moving of charge. Dou d bar by dou t is nothing but a displacement current that is existing in the circuit because of a time varying electric field, because d bar is the electric field. So the curl of h bar equal to conduction current density plus displacement current density. This is the modified Ampere circuit law. Now we are going to see the difference between the displacement current and conduction current density. Here we have taken the one circuit which consisting of resistance and capacitance parallel. The current passing through the resistor we have taken as I1. The current passing through the capacitor we have taken the I2. For this parallel branch, we apply the voltage which is varying with respect to the time. So whatever the current is passing through the resistance is different from the current passing through the capacitor. This current is nothing but conduction current. So the current passing through the resistor, I1 equal to J bar equal to IC by A, where J bar is nothing but conduction current density, IC is nothing but a conduction current divided by the cross section area of a conductor. This is equal to conductivity of a conductor into E bar. Assume the initial charge across the capacitor is 0, then the current passing through the capacitor IT equal to C into dV by dt. If we take that capacitor as a parallel plate capacitor, then C equal to epsilon A by D, where A is nothing but a area of a parallel plate, D is nothing but a distance between the two plates. Now in equation 2, you substitute the equation 3 and simplify, we are getting the I2 equal to sigma A by D into dV by dt, where V is nothing but the voltage impressed across a capacitor. Because of that voltage, there is an electric field will be existing between the two plates. There is a one relation between the voltage and electric field intensity between the two plates, that is E bar equal to V by D. V we can write it as a E into D. Now substitute the equation 5 in equation 4. We are getting the displacement current equal to epsilon A by D into derivative of E into D by dt. D the distance between the two plates, that is constant you can take outside. That is gets cancelled with a D in a denominator. So finally, we have a displacement current equal to epsilon A by derivative of E bar. Now this current is divided by the cross-section area of the capacitor that gives the displacement current density, that is equal to epsilon d by dt of E bar. Epsilon t E bar we can write it as a d bar, nothing but a electric flux density. So JD bar equal to dou d bar by dou t. This is the expression for the displacement current density. In this case, whatever the current is passing through the capacitor, that is nothing but a displacement current. The current is existing in the capacitor only because of a time varying electric field. Now the total current J bar equal to conduction current plus displacement current. Now substitute the current conduction current value and the displacement current value here. For the time varying field, we can write it as a conductivity of a conductor into E bar plus epsilon dou by dou t into E bar. In place of E bar, we can write it as E bar into e to the power of j omega t. If we differentiate that one, we are getting the j omega epsilon E bar. This is the total current which is passing through the conductor. The electric field is changing with respect to the time. If we find the ratio between the magnitude of conduction current to the displacement current, then we are getting the conductivity of a conductor divided by the omega into epsilon. Thank you very much. In this lecture, we have discussed about the what is the modified ampere circuit law for the time varying field.